The broadcast is now starting. All attendees are in listen-only mode.
Well, hello, everybody. Welcome to Coffee with Caleffi. This is Mark Olson. Glad you could join us. I'll be your presenter today. Happy to do that on our topic at hand. We have a good-sized group in attendance, or at least registered. People are still signing on as I'm speaking here. It's interesting what topics attract certain groups. So, for example, last month on Coffee with Caleffi, our topic was filling and purging hydronic systems. And guess what was the biggest segment of the market that attended that? Maybe you can think about that. It's contractors, by far actually on that topic. This month, on the other hand, the biggest segment is engineers, by far as well. So I find that somewhat intriguing, if not just interesting. So let's see here. So whether you're an engineer or a contractor or a manufacturer or a rep or a wholesaler or an inspector or a government official or a maintenance director, welcome. In fact, all of you are on this webinar from your attendance here today. So, and some folks from the international community as well. So welcome aboard, guys. Design journals for the new listeners, and we have several registered that we haven't seen before on this webinar. If you haven't seen Caleffi's Hydronic Design Journal, we make them available to the market free of charge. We mail them out every 6 months, and we're on issue number 23, as you see here, heat transfer and hydronic systems, which will be released in July. So I'm going to guess that most of the people on this webinar are intimately involved in heat transfer, and you'll enjoy that issue as well. This is a free subscription, by the way, and you can log on to our website and you can register to have these received in hard copy form to your desk. Okay, it's a pretty simple process. And I have them an open system here. The size of the water column squirting up out of the pumps is really to indicate the flow rate in each of these 4 circulators. And so what we want to have happen is that when one pump turns off of any of these 4, it doesn't increase the flow rate in the remaining open pumps or on pumps, such as this. And then when this pump that turned off turns back on, we don't want it to suppress. This would be an example of decoupled circulators in a system. What we don't want to have happen is pumps have been affected by that action of that pump. And when you turn off a pump in this, you typically have all the other pumps would increase in flow rate to some degree, even excessive. And that's one of the problems with the coupled pumps, is that your flow rate can exceed excessively the design flow rate for that circuit. And obviously there's issues potentially with that, including erosion, corrosion inside the pipe. So leakage as a result of the walls wearing thin and eventually leaking. That's erosion, corrosion, noise, and the circuit or the items that are in that circuit may not work correctly. Mind you, they have more flow than their design floor, at least for that application, and they might not even work properly. So those are issues with overflow. Underflow, well, this seems like it might be obvious. Underflow, you're not getting the heat transfer that you want that circuit to accomplish. So that's a problem with pump conflict. So when we look at ways of reducing or eliminating pump conflict and look at a very simple schematic here, we have a heat source. It could be a heat pump. It could be a condensing boiler, for example. And then we have 3 circulators sending heat up into our system and back. And if we have a high resistant type generator, as I show here, let's just talk about what could happen in application. So let's say, for example, we have 3 circulators on here, and 2 of these circulators are on, and they're pumping. Say these 2 right circulators pumping 5 gallons per minute up into the system. That flow comes back around to the return header and completing its journey around to the boiler to be reheated, etc. Now let's say this first pump kicks in. First pump sends flow up, comes back around, and comes to the return header. Now we've increased our flow significantly with that pump. Now we can't get all that flow like we'd like through the full flow arrangement here. And as a result of this bottleneck or restriction, there's going to be back pressure created against these return circuits, these connections here, which means back pressure against each of these 2 pumps. So whereby when this pump was off, these were generating 5 gallons per minute and things were happy. Now we might be 4 gallons or 3, or even suppressing flow almost entirely. So we have a coupled system. So what we want to do is we want to now create a primary secondary arrangement where we make a connection between these two T's and add a primary circulator. We have to add another pump here, otherwise the path that we have just created for flow from the secondary circulators by way of this connection bridge here, if you will, would be causing bypass and not flow going through the boiler. You would be starving the boiler. So you have to have a primary pumps, primary, secondary. Now this improves pump conflict, but it doesn't eliminate it. Why? Because our T's are fairly widely spaced here. You want to minimize the distance between your T's to minimize these pumps from seeing each other. So let's connect them together and you'll see something like this. Now we have a happy arrangement, well executed, closely spaced T's. Now our circulators up here, when they turn on and off, don't affect one another. So we have a good system now. Now a rule of thumb for how closely you should space these T's together. If your supply piping, in this case, is diameter D, you want to make sure your center to center connections on your primary are no more than approximately 4D, 4 times the pipe diameter. Then you should be in real good shape. The other thing on your secondary, to minimize any pump conflict, is you want, as you can see here, very generously sized headers. Okay, they look pretty thick there. So on your piping in your secondary, we call it short stubby headers. As close together as these pumps can be, the better, and to minimize the travel between your T here and your pump. Okay, short stubby. And then your common piping, that is the piping in your secondary that each of these pumps see, which would include from this point on your return all the way through back to here. You want to keep that average pipe velocity, your flow rate, such that your average pipe velocity is not much more than 4 feet per second. Doing so, you should be in pretty good shape altogether, minimizing any pump conflict. So let's take a look at an execution of this. This was actually a photograph that I used last month from Ohio, Mr. Burdick, and you can see we have a modulating condensing boiler over here. It might be 2, I think it's just 1. And we can see our primary pump pumping flow into our boiler, heating up the water. It comes out of the boiler, goes back out, and here's our 2 T's. Nicely connected together. Just think of the 4 times pipe diameter rule. Yes, that's abided by. And then out to our secondaries here, to our 6 or 7 secondary zone pumps, generously sized headers. So a very nice job from Mr. Burdick doing a closely spaced T arrangement. The second of the 3 methods for decoupling pumps is buffer tanks, as you see here. I've taken the T's away and put a buffer tank in place. Now you wouldn't do this just for the sole purpose of decoupling. This 4-port hydraulic or a buffer tank does perform decoupling or hydraulic separation, if you will, another term for decoupling, of these pumps over here. But the purpose of a buffer tank is to reduce the cycling that this heat source is going to experience, which is especially important in a highly zoned secondary, meaning you have several zones and at least a couple, 1 or 2 of those, even 1, with the heat load on that zone much smaller than the others. So in doing an arrangement this way, you reduce the taxing wear and tear on your, say if it's your heat pump, your contactors on your compressor inside of your heat pump, or in a condensing boiler, the on-off actuations that a condensing boiler will experience. Anything, if you can minimize on-off, you're going to improve the life. And in the case of the buffer tank, increase the efficiency of the system. So here's a execution of a buffer tank. This is a job that was down in Winston-Salem from a few years back from Energy Solutions. Thanks guys for submitting this a while back. It's a combi system. So what we have here is a buffer tank, and off to the right we have our secondary. So coming off the top of our buffer tank, heated water going out to, I think there's 8 different zones up to our building, coming back on his return header back to the buffer tank. Now this is the secondary side, okay? And by way of the buffer tank, having all these, at least 4 ports, these pumps now are decoupled. They don't see each other. Over on the primary side, we have 2 sources of generating heat. We have a heat pump. It's a ground coupled heat pump we can see, because against the wall here, we can see the polyethylene tubing going down into the ground. Let's see, which way would it be going down? This would be the return. Yeah, going down into the ground and the return back this way. Okay, so we got, it's actually a heat cool system in this building. We're just seeing the buffer tank that serves the heating side. When there's a call for cooling, there's a little diverting valve up here, and he will send chilled water over to a chilled water storage tank. So back to our example at hand here. So we got a heat pump, and then in those cold winter months when there's not enough heat in the ground to satisfy the heat demand of the building, then a backup heat source takes place. So the flow is this: secondary out, secondary return. The heat pump comes into one of the top connections and out from the bottom, and same thing with the boiler. The Caleffi buffer tanks have multiple ports that allow a lot of flexibility from an insulation standpoint. Now, before I leave this, just an aside, whenever you have from a buffer tank flow coming back to a heat generator, whether it's a solar collector or a heat pump or a boiler, you always want to draw from the coolest part of the tank, thus increasing the efficiency of the heat generator. Okay, so let's get on to hydraulic separators. I think we're doing pretty good on time. And that's the third of the 3 methods I will be talking about. A hydraulic separator does as closely spaced tees and a buffer tank. It decouples pumps. And so let's take a look at a photograph from an installation up in Ontario, submitted on Caleffi Excellence. So right in the middle, we see the Caleffi hydraulic separator. Off to the light circulators, so it looks like. So we have 5 zones. This is a radiantly heated chicken barn, if I remember right. And then we're having, so this is going out to our radiant slab and then come back to, so this is our secondary side of our system. This is with 2 boilers connected in parallel to the supply header going into the top of the hydraulic separator and returning back here, all right? So these pumps don't know that one another exists, and they certainly don't know that these guys exist by way of a hydraulic separator. And we'll get into the inside of what these things look like in just a few slides. Now, it's not just heating that you need to worry about pumps interfering with one another. Chilled water applications have the same requirement. And here's a job from Mr. Jose Adrian Lazo out at Santa Ana from Adrian Air. We were happy to have, he submitted this in. And he has, it's actually a 4-pipe system. So he's got heating and cooling. He's got Unico fan coils over here. You can see some really good attention to detail on his piping as well as his insulation. And on the left-hand side here, this is the chilled water side of his system. So he does a real good job. So coming off of the chiller, you can see marked in, call it gray arrows or maybe light blue, chilled water coming into the hydraulic separator, okay? The 4 or 6 zones over here are taking that chilled water up to the coils, absorbing heat, and then coming back here. So you got cool water here from the chiller, returning back to the chiller. Chilled water going out to your zones, and then the heated water back here. So the same holds true for chilled water as heating that is performed decoupling. Okay, we're going to do one poll question today, and I'm going to ask my guys if they'll run the poll. I'm not able to see it, but I'm going to read it to you. I have, in what applications have you used hydraulic separators? Heating, cooling, heating as well as cooling, so you've done both, or you haven't used hydraulic separators. And fifthly, if you're not involved in design or installation, check that one as well. So let's give it a few seconds and just see where things land relative to the use of hydraulic separators here amongst our North America, or listening audience, I should say, our global audience. So And I'll wait. I can't see the poll results. I'll wait for one of my guys to mention the poll results.
Hey, Mark, it looks like the answers are in. Heating, 47%. Cooling, 0. That's a little bit of a surprise, don't you think? Heating as well as cooling, 27%. And none, 22%. And the bottom is 4%. So almost half are for heating, and 27% for both.
Okay. All right. Well, I guess there's probably not a whole lot of guys out there that are doing only cooling. So our guys that are on the audience are doing heating as well as cooling, and in at least one application, they're using hydraulic separators. So that's really, really helpful to see. Thanks for running that poll. Okay, let's take a look at what the inside of a hydraulic separator is. So this is a hydraulic separator, also known as a hydro separator. And for the new listeners into this topic, it might be referred to as a primary, secondary, a decoupler. There's many words for a hydraulic separator in the marketplace today. They're all synonymous, but so our hydro separator looks like this. So what's going on is we have on our primary side, let's say in the case of a heating application, say from a boiler or a heat pump, we got heated water coming into our separator and returning back to the boiler. So this is our primary loop. Then over here, we have our secondary supply over here. Now you're wondering, your eyes drawn to all this color going on here, and you go, well, that's a lot of stuff going on in there. Well, there's a little bit going on there. Let me just walk through it. In the heart of a hydraulic separator, there is a flow straightener. You can see it here, a baffle plate. And what this is designed to do is that it is intended to make water laminar that otherwise might be turbulent in the event that you have vertical travel of fluid, either going up or going down, because turbulence translates to pressure drop, and that's something that we don't want to have. We want to minimize any pressure drop within the hydraulic separator, because that, after all, is what causes pump conflict. So it's a flow straightener, and you can see 2 helical arrows here. It's kind of an artist rendering. They would never happen like this in 2 different directions at one time. You're either going up or you're going down, or there isn't any flow. In the event that your primary flow rate and your secondary flow rate are equal, you wouldn't have any vertical travel of flow, okay? So they're designed to allow flow to be vertical, either in an upward fashion or downward fashion. And a baffle plate minimizes any turbulence. Now these baffle plates have a little bit of a perforation in them. You see these little holes perforated in them. This gives us a little bit of what's called coalescing, and you can see air bubbles that are actually coalescing to out and up through the air vent. We'll talk more in detail about a dedicated coalescing separator in just a few slides. So and down below here, you see debris coming in off your secondary. Typically, debris in a hydronic system has a specific gravity higher than water, meaning it will sink in water. And because you are slowing down the velocity of the fluid as it enters into any type of chamber like this, you get some separation, but not dedicated for dirt elimination. So the primary function of a device like this is hydraulic separation. But secondarily, you do get the added benefit of some air separation, in some cases adequate enough to have no other air separators on your system, and some dirt removal simply by trapping it down here. We'll come back to this slide because we're going to show a cross section of another hydraulic separator that has added functionality inside of it, and you'll see what that looks like. So what is that added functionality that's available for people in the marketplace today? Well, one is coalescing air separation, which is a very efficient way of getting rid of air in a system, and then high efficiency dirt separation. Also, magnetic separation is another option in hydraulic separators today. Okay, why are we worried about air? Well, what's the sources of air in a hydronic system? Well, firstly, the initial fill of the system and any makeup, that mains water supply has air in solution, and the air in solution is waiting to come out of solution as soon as it is heated up or undergoes a sufficiently large enough pressure drop in your hydronic system. And that's what we want to take advantage of when we eliminate air out of a system, that property of air coming out of solution. So first and foremost, the biggest source of air is the initial fill, and then also makeup. Certain systems like radiant systems or any system that has non-oxygen barrier tubing, it doesn't necessarily have to be just PEX, but it could be polyethylene used in geothermal systems, You have different type of polymer piping now, very common in the marketplace, not oxygen barrier, by the way. So oxygen is going through the walls of that type of polymer by way of osmosis. And it's very interesting, but it actually happens. But also as the system ages and gaskets start to wear and develop leaks and O-rings, as that water leaks out or fluid leaks out, it's an opening for air to get in. But probably more importantly, as water leaks out, what's going to happen is that your pressure reducing valve or your pumping makeup cart is going to sense that, and it's going to open up and allow cold water in the case of a straight water system. And that water is going to have oxygen. So those are air sources that we have to be concerned with. And the biggest problem with air is corrosion, quite frankly, typically, secondarily, probably noise in certain hydronic systems. So manufacturers like Caleffi have coalescing air separators. What is coalescing? It's the process of taking advantage of microbubbles being created from coming off of a boiler, for example, or even on the return leg back to a chiller after it's given up its heat in your terminal units, and collecting that air by way of adhesion. Those microbubbles actually adheres to these sharp surfaces inside the separator. And those small microbubbles collide, creating a bigger bubble, but they continue clinging until eventually the buoyancy force from the larger bubbles now overcome the static cling force against the mesh. And then they float up into the chamber, and the float opens the linkage and out goes your air. That's how air separators work. Now, as long as I said, it didn't take that long. It's a very quick process if you ever saw demonstrations of this from any manufacturer. Now, here's a look at what those meshes look like. This might be taken from a 2.5 inch unit. This is the barrel that you see here, very sharp edges. That's a stainless steel mesh from Caleffi on my desk. I actually cut myself on that. So jumping to the functionality added in today's hydraulic separators, here's a photo that would depict opportunity in today's world. It's a Caleffi hydraulic separator, creating separation of all these 5 or 6 primary circulators from these Baxi condensing boilers, nicely sized headers, by the way. And then along the left-hand side, we see, you can't see, but there's several zones, mini circulators driving up to deliver heat into the building. So the hydraulic separator has decoupled all of those, but the designer wanted to have dedicated coalescing air separation, so he added a second component on a Caleffi discal air separator. He would not have to do that in today's world with functionality built into the hydraulic separator. I'll show some of that in just a second, but let's talk about the other side of the separator called the dirt. The dirt side. Where does dirt come from? Well, on-site machining processes, cutting threads, shavings, pipe string, pipe tape. Obviously, solder is a very big source of, we'll call it dirt, let's just say debris, things that we don't want in our system. Solder slag, even dirt. I joke. These guys down in New Mexico that was doing a ground source heat pump installation. So anyway, dirt gets into our system by many means, and traditional means of getting rid of debris in a hydronic system is basket strainers, otherwise known as Y strainers. So fluid would come into a Y strainer, down into the little cartridge here, or mesh, I should say, and back out through the continue on in the circuit. Now, as these do their job and begin filtering out any debris, they start plugging up. And as they do, pressure drop starts to occur across the mesh or across the Y strainer. And as a result, your flow rate is suppressed, even to the point where it's detrimental. So they need to be maintained. And so when they are clogged up, you'll get more of a pressure drop. And it's always wise to isolate your Y strainers with ball valves if you're going to use them. Put pressure gauges on either side and monitor your pressure drop across your Y strainer. When do you change them out? Well, we recommend that if you don't have any other criteria, whatever is the differential pressure of the circulator driving flow through that Y strainer, let's call it 10 feet ahead, at 5% of that value, if you have that pressure drop of, in this case, it would be what, half a head, right? One half foot ahead. You would have time, you would need to change that out. Then you'd have to close the ball valves off and then clean it out. That's how you would do basket strainers. So they have their purpose. We like them not so much down in the mechanical room where you might find a device that is in front of you now, but more up in fan coils and up high where you don't have quite as much of an issue with debris. Down below in the mechanical room is where you want to have your dirt separation. And these are called low flow zone dirt separators. There's probably, I think in North America, maybe 3 manufacturers that are active in the marketplace with this type of separator currently, could be more. So how they work is as fluid velocity enters into the separator, it slows down. So by a factor of about 9 or 10 to 1. So if we have 10 gallons per minute coming in, it slows down to 1 gallon per minute as it goes through. And simply by gravity effect, we start having debris drop out. Also combined with the deflection of the mesh here, it gives us the separation so the fluid continues down through the system. And as the separator does its job getting rid of debris, unlike the Y strainer, which starts to clog up, the debris gets dropped away from the flow path. So you don't have any buildup of, you don't have an increased pressure drop that occurs as it's doing its work. And they have a lot more, obviously, volume here. So it lengthens the interval times versus a Y strainer. And then lastly, you don't have to take these offline in order to service them. When you want to blow them down and open up the ball valve, there's no need to isolate them off. Of course, you got to have makeup water to replenish anything that you purge off here. So that's low flow zone dirt separators. And so going back to our standard hydraulic separator here that we talked about, whose primary function was hydraulic separation, and secondarily, it does some air and dirt removal. Today's separators would be something like this. In the case of Caleffi's world, a 3-in-1 device, 3 functions. We call it a HydroCal. So on the top, we have taken the baffle, replaced it with a specially designed mesh, stainless steel mesh top to bottom. In the top portion up here, we have dedicated air separation, coalescing air separation. So high efficiency air separation as you would a dedicated air separator. Down here, we have dedicated high efficiency dirt separation as a dedicated dirt separator would do, and also hydraulic separation. So we're decoupling our pumps. And so its primary function is actually all 3, hydraulic, air, and dirt separation, all in one. So let's take a look at least one photo. Here's from Young Services, Mark Young, Glenwood Springs. And you can see at center is the HydroCal 3-in-1 device. Here's our primary side of our system. We have 5 or 6 condensing boilers over here in parallel, feeding into the supply header, going into the hydraulic separator. So here's our primary ins, our hot water in, cool back. And our secondary, we have a couple of pumps over here going out to our system and then back. These are decoupled and these are decoupled. And notice there isn't any other dirt separators or air separators on the job. Okay, so let's look at some pricing, if you will, or value. We say it, value without performance compromise. So if you do some comparison and using, for example, Caleffi's 4-inch list price comparison, okay, of a 3-in-1 device, which is represented here and here, we could individually have a hydraulic separator shown here, which is listed in our current catalog at $7,100. That's list price, by the way. And these are ASME certified models. We also offer non-ASME models, a little bit less expensive, but this is the ASME for comparison. Dirt separation and air separation. So if you add up these 3, if you were to install those in a system independently, it'd be $17,000, well, $17,500, maybe something like that, $1,000 versus $9,300 on your HydroCal. So you can see the value, not just in the componentry, but also the labor in connecting pieces that needs to make these things go together. A lot of savings there. And before I leave this slide, you'll see what's this here? Well, it's a half shell. It's our insulation jackets that come standard on all our smaller hydraulic separators, 4 inches and down. Okay, very nice insulation, by the way, pretty thick, so they do a good job. This is quite a bit of surface area on the hydraulic separators, typically in your mechanical room, and so they will radiate heat, obviously, and become a big heat radiator. So it's good to, when possible, to insulate your hydraulic separators because in comparison to the surface area of all the piping in your mechanical room, there might be more surface area on your hydraulic separator alone. So a question came in before the webinar, how do you size a hydraulic separator? Well, it's pretty straightforward, and here is the criteria. So you determine your max flow rate, or otherwise known as your design flow rate, in your primary side of your system, and then also separately in your secondary side, your distribution side. And the greater value of the two determines which size separator to use in your application. So for example, if our primary design flow rate is 1,200 gallons per minute and secondary 1,700 gallons per minute, which isn't untypical, having your primary lower than your secondary in application, then the secondary circuit is the criteria, and we can see we would have to choose a 12-inch pipe diameter hydraulic separator to accommodate that 1,700 properly. Okay, so pretty straightforward. And all of our hydraulic separators, whether it's a standard hydraulic separator or one that has built-in functionality, they have the same type of sizing criteria, nothing unique. We do the work for you on that. Hydraulic separators do more than decouple pumps, is our topic of our webinar. I don't think I even said that. Now I'm saying it. But jumping to magnetic separation. Now, magnetic separation is, here in North America, fairly new, been around in Europe for quite some time. And why do we even worry about it if it was fairly new? I mean, it's not an issue, right? Well, let's get into magnetic separation. Where magnetic separation plays, it's in the debris in a system that happens as a result of the aging process. Basically, the system beginning to experience some corrosion. All systems will experience some corrosion. Any hydronic system will experience some corrosion. And the most notable metal to be worried about is ferrous metals. So think about any hydronic system. Even if your hydronic system has stainless steel heat exchangers inside of your modulating condensing boilers or your heat pump, and you have all copper piping, and your terminal units are aluminum or copper or both, think about all the other things that could be steel in that. Your pumps, your volutes in your pumps are typically going to be cast iron. Your expansion tank, on the inside of your expansion tank, away from the bladder, is going to be what? Some ferrous metal. You probably can think of others. So there's going to be some metal, ferrous metal, that is going to have experienced some corrosion. Now, corrosion isn't necessarily bad. It just needs to be controlled. In fact, iron, when it experiences some level of corrosion, the oxide layer that builds up as a result of the corrosion can act as a barrier to any further corrosion. The key thing is to keep your oxygen, dissolved oxygen content to a minimum, and that's this guy right here. So what we're doing is we're showing water inside of a system touching some ferrous metal part, be it iron or steel. And so dissolved oxygen is the catalyst. It is what creates, it's the horsepower of corrosion to take place. And it sets off a chain reaction of chemical reactions, if you will. But the upshot of it is ferrous oxide gets created. And we're looking at a very microscopic level right here. You wouldn't even be able to see this with the human eye, but we've blown it up to show you chemically what's happening here. And you wouldn't have it happen only in one spot. It would actually be happening concurrently, uniformly across the metal, and generating what would be a surface that would look rough from microscopically, but from a distance might look still smooth. But what happens if you have an ongoing process of oxygen in your system, then the corrosion continues unimpeded and begins to slough off and starts to float around. And that corrosion or that debris is called ferrous oxide, and it exists in a hydronic system as in the form of typically magnetite. And here we see some ferrous oxide being drained from a couple different systems. This one is a little bit redder and this one's a little bit blacker. They're both ferrous oxide. It just happens that this one is likely a system that has still significantly great amounts of dissolved oxygen in it. So there's probably a source of a lot of oxygen getting into this system, because this system hasn't finally reached equilibrium, and it's getting purged out here. This is called hematite, and this is actually over here called magnetite. Think of hematite, a lot of oxygen. It'd be like your blood, hemoglobin. You know, as blood leaves your lungs and is fully oxygenated, it's bright red, right? But as it gives up its oxygen through your body and comes back to your lungs, it's darker color. So you can think of the same analogy in a hydronic system. That aside, this is iron oxide, and it's problematic in a system. And it can, because of the nature of iron oxide, it exists in the system in a very, very small particle form. In many cases invisible to the human eye, but if you put it underneath a microscope, it looked like a kidney stone. It has all kinds of jagged edges on it, and it's very dense, and I mean it's very hard, and as a result, very disruptive. O-rings, it likes to be sticky, so clogged pipes, and because it's magnetically attracted to magnets, here is a ECM circulator whose rotor was pulled out, and we can see it stalled, and we can see magnetite here. So as a result of that ECM magnets on that rotor attracting the magnetite, and eventually she stalls out. Bob, by the way, or whoever, one of our managers, cleaned it up and put it back into service, and it worked fine. So that's why manufacturers have, well, at least in Caleffi's case, we have magnetic separators that, in addition to non-magnetic dirt separation, also do magnetic dirt separation. And you can see what's happening here. We have a specially designed separator with a stack of rare earth magnets stacked on top of one another. These are called neodymium ferrite. That's hard to get out. And this stack is inside of a brass sleeve up into the belly of the separator. So that tricky magnetite that's so small, and even though it's denser than water and you think might fall down, it gets carried in a fluid path very easily and continues on in the system, only to find itself in a place that it shouldn't find, and creating problems like I showed you in that previous slide. And so that's why there are magnetic separators. They articulate as you service the separator. When you're going to blow it down, you pull the magnet out, and if you have no clearance in your floor, they'll articulate like this to give you the floor clearance. So nice design by our engineers. And to give you an idea, if it's the first time you've seen these, how powerful these are, is by just taking two magnets, a section of our stack here, and connecting it up to a barbell or a 10-pound weight that Cody's done here. You can see the strength of these magnets, and this is just two magnets. Imagine a bunch of magnets inside of the separator working. And here's one in action down in Kenosha, cleaning up a job, a dirt magnetic separator getting purged off. Now that takes us to our last separator in terms of added functionality. We call it a Sep 4, because in addition to air separation and dirt separation and hydraulic separation, it also has magnetic separation. You get them all for the price. You get them all, they all come together. And so it looks like this. And so instead of a stack of magnets going up to the belly, like I showed in that commercial example, there's a band that goes on the outside of the brass here. And this is a nice, very nicely job done years ago before these separators were even available. And I imagine if this designer were to do this again, he would save himself a lot of material by simply combining these three, this air separator, dirt separator, and hydraulic separator into one. And on the inside, they look something like this here. Air separation, dirt separation, hydraulic separation, and the added benefit of making sure any corrosion effects get taken care of too, magnetic separation. Here's a job showing in action a Sep 4 taken from New Bedford, Massachusetts on Caleffi Excellence Program, Michael Grella, right in the middle here. Two boilers in parallel. These pumps are decoupled. All these pumps on the secondary side are decoupled as well, and no other air separators or dirt separators needed on the job. Nice job there from Mr. Michael. Another job done up in Saskatoon. This is a Sep 4. Now these are residential. I'll show you commercial here in just a second. And I wanted to point out up here is a temperature gauge. So on many of our hydraulic separators, we have a port right there at the mix point. And it's nice and convenient to use that port to place a dry well in, where you can insert a temperature gauge and keep an eye on the temperature out here on the secondary, okay? Some manufacturers or some boilers actually have a temperature sensor probe that they control the secondary temperature by that actually sticks into a dry well right there. Or similarly, you could strap it onto your secondary here. So nice job up here in Saskatoon. Gets at least what 5, 6, 7 secondary zones over here. Down here we see a pumping unit, so we know this is probably a glycol system, so there's no mains water coming in. And it's especially important in glycol systems to have high efficiency air separation like you have in a SEP4. Why? Glycol is a oxygen scavenger, and to the extent that oxygen gets into a system, as glycol absorbs oxygen, as we've shown in other webinars, you will start to see the pH begin to drop. Basically, the glycol can become acidic. So to the extent that air gets into any type of glycol system, you want to get it out, like Mr. O'Neill did right here with the SEP4. Now jumping to our commercial size SEP4, this is Cody, it's a screen capture. If he sees this when he comes back from his travels with his eyes half closed, he'll kill me, but, or somebody. So Cody's doing a video here that was posted. We have installation tip videos for all of our products. And you can see here in our bigger separators, to get the horsepower, if you will, our magnetic horsepower we need, we needed to have more than just one stack. And so there's 3 stacks. And so Cody is showing how the stacks come out when you want to blow down the separator of its collected debris. It's probably what 18 inches or 20 inches long. It goes up into the barrel, and here you have a good photograph of, or picture of the brass dry well. So the stack always stays dry. It's up in the dry well. Now, why do we use brass here? Well, magnetic flux lines that are needed to attract magnetic debris, the corrosion effects, pass quite freely through brass, but they don't through a lot of other metals, including ferrous. In fact, they're disrupted by ferrous metals. So that's why we use a thin-walled brass sleeve up through the belly of our commercial units. Now, getting back to here, this photo, you can see in the background, you see a bunch of our separators over here, but you can see if you squint your eyes, a smaller separator, but this is a combination air and dirt magnetic separator, and it only has 1 magnet. So I think it's at 6 inches is our cutover point where we go from 1 magnet, and from 6 inches up, we go to 3 magnets to get that power I mentioned to you that's required, okay, to do a good job. I think we're doing good on time, and we're going to have some time left for questions. So here is a job of a SEP4 from Texas. It's over here on the left-hand side, sitting pretty. And connected to it are several boilers. You can see 3 of them here. There's 2 or 3 off to the right here, but the photograph couldn't get them in. So they're all feeding into a supply header that drops down and goes into the top of the hydraulic separator, okay, delivering the heat, coming back to journey back to the return headers, back to each on the header, on the return back to all of these boilers. Now you might say to yourself, well, these don't look like boilers that would need a hydraulic separator, because they look like non-condensing boilers, and if you said that, you probably have a pretty sharp eye. And you are correct. These 3 boilers do not, these are non-condensing boilers. They wouldn't be hurt by a hydraulic separator. They probably have less restriction in them than a condensing boiler, but you can tell they're non-condensing because they have these blue items here. These are that make sure that the return water back to the boiler stays above the temperature in which dangerous flue gas condensation can occur, destructive condensation. So these are just big units doing that, these 3 thermostatic mixing valves that perform that function. Now, okay, off to the right here though, and does a lot of these systems down there in Texas are condensing boilers. Okay, now think of where you're at. You're down in Texas. You don't have a long heating season. Condensing boilers are typically, in this case, for these size units, more pricey, but they're significantly more efficient. So most of the season down in the Houston area, you don't have a peak season lifting. They're more expensive, but they're more efficient to operate, more cost effective. But as the winter pushes into December and January, and your target heat, your temperature over here, your heat load of the building increases, and the condensing boilers can't keep up, then the non-condensing boilers come online. So this is all controlled as part of a system. I believe it's one control system that the manufacturer has for both the condensing and non-condensing boilers. So nice job from Goes down in Texas. Okay.
Nice job, Mark. I do have a few questions here. Mark, will ghost flow occur if there is a domestic hot water, a DHW priority or piping demand on the primary side, but no space heating demand, or I guess no secondary demand? So can you get ghost flow occurring across a hydraulic separator in that case?
Okay, that's an interesting question. So I think it's a good question. So I'm just going to pop this installation here. So if we have, and disregard the air separator over here, but if we have a hydraulic separator and we have a domestic hot water demand connected into our system, let's say it's on our primary side, all right, and coming back, it could be on our secondary, but most commonly you would connect your domestic hot water on your primary side, ensuring the highest temperature water being delivered to the hot water heater. So the question is, I think if you have a domestic hot water call and you don't have any heat demand, could you create ghost flow, which I think he's referring to? Would these pumps, let's say we just have a one boiler system, with no demand, would you inject flow into your secondary because you want to satisfy your getting flow out to your direct hot water heater? And the answer to that is no. The hydraulic separator is sized so that even if you have no flow over here, because of the generously sized diameter in the barrel, that's that vertical part, you would not have any ghost flow going in here. So Mrs. Smith's kitchen in the summertime would not get heated inadvertently. So hopefully I understood and answered that question right.
Okay, good, thanks. Here's a question. Can I use a hydraulic separator as a buffer tank? I think that, can I use a hydraulic separator sort of as a mini buffer tank is the question.
Okay. Well, let's go to this and try to address that. Okay. So if you're wanting to use a hydraulic separator as a buffer tank, you could only do that if your zones are very small. You'd have to have some very small zones. In fact, because even though a hydraulic separator does hydraulic separation and there is some fluid in the separator by way of the barrel being pretty wide diameter, the amount of energy in that hydraulic separator that it can store in relationship to how much heat is needed for the zone to be satisfied is insufficient. So a hydraulic separator, unless you had a very large hydraulic separator put on your system, on your small system, it would not work very well.
Okay. Where would you not use a hydraulic separator?
Where would you not use a hydraulic separator? Good question. Many places you wouldn't use a hydraulic separator. And so let's just talk about this one here. So I can think of a few. First of all, if you have let's say a boiler, and your boiler is a large mass, say a oil-fired cast iron boiler, typically large mass, meaning very little pressure drop through the boiler as fluid comes into the boiler to be reheated and back out. As a result, these pumps wouldn't see much resistance as relates to going through the boiler. So in that case, you wouldn't need primary, secondary. And many systems go in that way these days. Cast iron boiler, no need for primary, secondary. Another example is some manufacturers are saying that if appropriately designed, the secondary system on a condensing boiler, it can accept full flow, meaning it can accept 100% of the design flow created by your pumps up here, meaning it also can accommodate full flow through the condensing boiler. Now, I don't know the models offhand, but I do hear that from time to time on some models of some manufacturers. A third example that I can think of in the heating and cooling world is in a, say it's a typical centrifugal chiller application. As I mentioned, chilled water has just as much need for decoupling of pumps as heating systems. But in those big chilled water systems, until now, it's often been most economical to create a bypass here, if you will, simply by using piping and having the piping sized in diameter wide enough to accomplish the task of minimizing pump conflict. Okay, and those would be three examples I can think of. Now, you could use a hydraulic separator in that case, and you get the added functionality, especially in a 3-in-1 or 4-in-1 device, of all the other benefits like air separation and dirt separation. And you might even be better off that way. But that would be an example where just a pipe, a decoupler pipe, sometimes seen on drawings, can be used instead.
You want to close it out?
Yeah, I'll close it out. So I want to thank everyone that attended today. Come see us again next month. Mr. Matt Baker from TM Sales is going to talk. And if you want to learn about ECM pumps, different operating modes, this is the place for you. So tune in June on Coffee with Caleffi. Until then, have a good day, and thanks for joining. Bye-bye.